In this episode, we're going to take the idea of detection and turn it into something you can reason about instead of something you either trust blindly or dismiss as noise. Most beginners start with an understandable assumption that security monitoring should work like a burglar alarm, meaning it should go off only when something bad happens and stay quiet the rest of the time. Real detection systems do not behave that neatly because computers are busy, networks are messy, and attackers often try to look normal. The result is that detection is a constant balancing act between seeing enough to catch real threats and not seeing so much that every alert feels like a false alarm. When people say a detection program is good, they usually mean it has been tuned, which is a careful process of making choices about what to look for, how sensitive to be, and where blind spots still exist. If you can understand signatures, anomalies, false positives, and coverage gaps as parts of one connected picture, you'll be able to evaluate detection systems with mature skepticism and practical confidence. A thoughtful place to begin is to define what tuning really means in the context of detection. Tuning is the process of adjusting detection logic so it better matches the environment it is protecting, because no two environments behave exactly the same way. The same signal can be normal in one network and highly suspicious in another, and a detector that ignores that reality will either flood you with alerts or miss important events. Tuning includes setting thresholds, deciding which events deserve alerts, enriching alerts with context, and suppressing patterns that are known to be harmless. It also includes making sure alerts arrive with enough detail that a human can act on them without guesswork. Beginners sometimes assume tuning is just making alerts quieter, but good tuning is more like focusing a camera. You are trying to make the picture sharper, not simply dimmer. When tuning is done well, an alert becomes a meaningful story starter rather than a vague complaint that something feels off. Detection approaches often get grouped into signatures and anomalies, and understanding the difference helps you predict both strengths and failure modes. A signature is a recognizable pattern that is associated with something known, such as a specific exploit technique, a malicious file characteristic, or a particular command sequence. Signature detection can be very effective because it can be precise, and when it matches, you often get a clear explanation of what it thinks it saw. The downside is that signatures are tied to what is already known, so attackers can sometimes evade them by changing small details or using new methods that don't match the pattern. Anomaly detection, on the other hand, focuses on behavior that looks unusual compared to a baseline of normal activity, such as a device suddenly sending far more data than usual or a user account logging in at strange times. Anomalies can catch novel attacks, but they are more likely to produce noisy results because unusual does not always mean malicious. Thoughtful tuning is about using both approaches in a complementary way rather than treating one as a complete solution. To make signature detection feel practical, it helps to picture it as pattern matching with a very specific vocabulary. A signature might look for a known sequence of bytes in network traffic, a known structure in a document attachment, or a known set of steps in an attack chain. Because it is looking for a specific pattern, it can often say something like this resembles a known exploit attempt against a particular kind of service. That specificity is valuable for quick decisions and for learning because it can teach defenders what threats exist in the wild. The tuning challenge is that a signature can be too broad and match harmless activity, or too narrow and miss slightly modified attacks. In a busy environment, overly broad signatures can generate constant false alarms, which trains people to ignore alerts. At the same time, disabling a noisy signature without understanding what it protects can create a hole that attackers can walk through. So tuning signatures is about precision, context, and discipline change, not about turning off anything that is inconvenient. Anomaly detection feels different because it is less about matching a known bad pattern and more about measuring deviation from expected behavior. The heart of anomaly detection is the baseline, which is your best guess about what normal looks like for users, devices, services, and network flows. Baselines can be built in many ways, but the conceptual point is that they rely on historical patterns and assumptions about stability. This is where beginners often get tripped up because they assume normal is a fixed thing, when in reality normal changes with business cycles, seasonal activity, software updates, and human behavior. An anomaly might be a real attack, or it might be a new business process, a backup job running at a different time, or a software rollout that changed traffic patterns. Tuning anomaly detection, therefore, includes constantly refining what normal means and making sure the system has enough context to distinguish new legitimate behavior from suspicious behavior. When anomaly detection is tuned well, it becomes a spotlight on meaningful changes rather than a panic button for anything unfamiliar. Now we need to talk about false positives and false negatives, because these are not just annoying statistics, they are the lived experience of detection. A false positive is an alert that claims something is suspicious when it is actually benign, and the harm is that it wastes time and erodes trust in the monitoring program. A false negative is when something malicious happens but the detector fails to alert, and the harm is that the organization remains unaware while damage continues. Beginners sometimes think the goal is 0 false positives, but that goal is unrealistic and even dangerous, because making a detector perfectly quiet often means making it blind. The real goal is to reduce false positives to a level where humans can respond reliably, while keeping sensitivity high enough to catch important threats. This is why tuning is a balancing act, not a one-time setup task. Every tuning decision shifts that balance, and mature teams treat the balance as something they manage consciously rather than something they hope will work out. A practical way to understand tuning decisions is to think about the cost of being wrong in each direction. If a particular type of alert is noisy but represents a high-impact threat when it is real, you may accept some noise and invest in better filtering rather than disabling it. If another alert is noisy and represents low-impact issues, you may choose to reduce sensitivity or route it to a lower priority queue. This is not about ignoring security. It is about aligning attention with risk, because attention is a limited resource. The environment matters too, because some organizations can tolerate more disruption than others, and some systems are more sensitive than others. Tuning, therefore, includes prioritization, which is the act of deciding what is urgent, what is informational, and what is useful only in combination with other signals. When prioritization is missing, everything looks equally serious, and that usually means nothing gets treated seriously for long. Coverage gaps are the part of the detection conversation that many beginners overlook, yet they are often the reason incidents succeed. A coverage gap is any area where the detection program has limited or no visibility, such as unmonitored endpoints, blind network segments, missing logs, or activity hidden inside encryption where no supporting signals exist. Attackers tend to find and exploit these gaps because they prefer to operate where they are least likely to be noticed. Coverage gaps can be technical, like not collecting authentication logs from a critical system, or architectural, like allowing traffic to bypass choke points where monitoring is strong. They can also be organizational, like not having ownership for certain systems, so nobody ensures logging is enabled and forwarded. Tuning is not only adjusting what you detect, it is also understanding where you cannot detect and then deciding how to reduce that risk. When teams tune alerts without addressing coverage gaps, they can end up with a beautifully quiet dashboard that still misses the most important activity. One common coverage gap arises from relying too heavily on any single data source, especially network-only visibility. Network traffic can tell you that systems communicated, but it often cannot tell you what process initiated the communication or what user context was involved. Endpoint and identity signals can fill that gap by showing what happened on the device and who was involved, but only if those logs are collected reliably. Another coverage gap arises when traffic is routed in ways that bypass central monitoring points, such as direct internet access from segments that were assumed to be controlled. A third gap comes from unmanaged devices, where you have little control over logging and patching, but those devices still connect to the network and can be used as footholds. Thoughtful detection design tries to overlap these perspectives so that when one view is limited, another can provide evidence. In practice, that overlap is the difference between a quick, confident investigation and a long, uncertain guessing game. Signatures and anomalies also interact with coverage gaps in a way that matters for tuning strategy. In areas where visibility is limited, signatures might not trigger because the detector cannot see enough detail, and anomalies might be unreliable because the baseline is incomplete. For example, if you do not collect enough historical data on a segment, anomaly detection may flag everything as unusual, which creates noise that people stop trusting. Conversely, if you rarely see a particular type of traffic, You might mistakenly treat it as harmless when it appears, even though rarity can be a useful risk indicator. Tuning, therefore, includes deciding where anomaly detection is appropriate and where signature detection is more reliable, and sometimes where neither is sufficient without additional collection. This is why detection engineering often starts with questions about data quality, coverage, and context rather than jumping straight to alert logic. If the underlying signal is weak, tuning the alert is like polishing a foggy window and expecting a clear view. Another subtle but critical topic is the difference between detection that is technically correct and detection that is operationally usable. An alert can be accurate, yet useless if it arrives without context, lacks a clear reason, or cannot be investigated with available tools and data. A beginner might assume the detector should do all the work, but in reality, the detector is a pointer that guides human attention toward a potentially important story. Tuning for usability includes adding context such as the affected asset's importance, the user involved, the recent related events, and whether the activity matches known business patterns. It also includes reducing duplicate alerts that describe the same underlying event, because duplication inflates noise without increasing insight. Good tuning makes alerts actionable, meaning the responder can take a next step confidently, such as checking related authentication events, reviewing recent changes, or isolating a device if the evidence warrants it. When alerts are not actionable, they create fatigue, and fatigue is a security weakness attackers can exploit. It's also important to understand that tuning is not purely technical, because humans are part of the detection system. If responders are overwhelmed, they will triage faster, make more mistakes, and miss patterns that require careful attention. If responders do not trust alerts, they will delay action, and attackers benefit from delay. Tuning, therefore, includes the human loop, which means aligning alert volume with staffing, aligning severity with true risk, and making sure the alert language is clear enough to be interpreted consistently. This is why mature detection programs develop playbooks and consistent decision-making criteria, even when the tools are sophisticated. For beginners, the key lesson is that a detector that produces 1,000 low-quality alerts is worse than a detector that produces a handful of high-quality alerts, because the first one trains you to ignore and the second one trains you to act. Thoughtful tuning aims to build that positive training effect. When you put all of these pieces together, you can think of tuning as a continuous cycle that combines measurement, adjustment, and validation. You measure what alerts fire, how often they are true, how long they take to investigate, and what kinds of incidents slip through undetected. You adjust signatures by refining patterns, tightening scope, and removing outdated rules that no longer match real threats. You adjust anomalies by refining baselines, adding contextual filters, and choosing thresholds that reflect normal variability. Then you validate by checking whether the changes reduced noise without creating new blind spots, and whether responders feel more confident rather than less. This cycle is not glamorous, but it is the work that makes detection real instead of performative. A tuned system is one that reflects the environment's reality, not one that reflects a generic template from somewhere else. That is why tuning is often described as engineering rather than configuration. As we conclude, the main takeaway is that detection quality depends far more on thoughtful tuning and honest understanding of limits than on any single detection technique. Signatures can be precise and fast, but they are tied to known patterns and can be noisy if written broadly or stale if not maintained. Anomalies can catch unfamiliar attacks, but they rely on baselines that must be curated, and they can generate noise when normal behavior shifts. False positives and false negatives are not just statistics. They are the forces that shape responder trust, response speed, and overall program effectiveness. Coverage gaps are the silent risk that can make a well-tuned system still miss the most important events, so tuning must be paired with deliberate visibility planning. When you approach detection as a living system that blends technique, context, and human usability, you end up with monitoring that actually helps you win, not dashboards that merely look busy.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.